Alright, so we're going to take a look at linear regression t intervals in this particular video. Going to be using your calculator again, so make sure you have that out. And we're also going to go over a mini-tab output look at what's going on with this. So let's advance to the next page and take a look at what's going on. Alright, so I have given you a set of data here. Take a second and input that in your calculator, and then we'll take a look at the 4 conditional checks for this. Alright, so go ahead and put that in and then come on back. Okay, so you have that information in, and with any confidence interval we always have to identify our population of interest and our parameter of interest. So our population of interest, that which we are sampling from, are Major League Baseball teams. And our parameter of interest is total runs in a year given the team batting average. So we're going to be looking at a slope. We're going to be looking at change in runs over change in average. And so that you know, change in runs over change in average actually yields total runs in a year. So that is what we're going to be looking at. We're essentially looking at the slope again. We're going to be doing a confidence interval on the slope where the numerator of the slope is change in runs and the denominator of the slope is change in average. And we want to go through our 4 conditional checks again. They're the same 4 conditional checks, so we're looking for evidence of linearity. We're looking for independent observations via an SRS. We're looking at that variation about the line, so we're going to be looking at the constant distribution of residuals, and then we're going to be looking at the normality of the response variable, so either taking a look at a histogram or a linear probability plot, and in this case we're going to look at the linear probability plot of the residuals. So pretty much here is all the information that you need to be able to go through the conditional checks. So in the upper left-hand corner here we have the linear regression performance on list 1 and list 2, and we notice a strong R and R squared value. We also notice our slope and our A value, and I'm going to tell you right now that I did that backwards. I did the old Lin-Reg number 4 instead of number 7. So the slope that we're looking at is actually going to be the 5709.2429 number, and the y-intercept is actually going to be the negative 706.2313. So if you used the wrong linear regression, you have the same numbers I have. If you use the correct ones, you have the ones that are written in red. We also see that the graph is definitely looking linear. It's definitely a positive association between the two. I guess the higher your team average, the more runs you scored. That makes sense. We also see that we have our consistent looking residual plot. First of all, it supports the linearity by being scattered, but it also has a fairly even distribution above and below the line for our entire domain. And then this is the normal probability plot over here of the residuals, and you'll see that it's a fairly linear association between x and the residuals, meaning that we have a normal variation of the y's. So our conditions are met for this. I would reference these in my conditional checks, so commenting on the normal probability plot, maybe even doing a little sketch of it, but definitely saying that the normal probability plot for the residuals is approximately linear. Get that down as one of your 4 conditional checks. So we know that any confidence interval follows the same general setup, that we have a statistic plus or minus a t-star value and a standard error value. And remembering that when doing any linear regression problem, we're going to be using n minus 2 degrees of freedom. So we are going to do a 99% confidence interval for this, and we might as well go ahead and fill in what we know. So we know that our b value was 5709.2429 plus or minus our t-star value. We're going to be doing a 99% confidence interval at n minus 2 degrees of freedom, so that's going to be at 14 degrees of freedom because we had 16 initial inputs. So to get our t-star value, you can do a little inverse t on your calculator, and we're going to be doing the 99%, so that means that there is 0.005 area above, and we're doing that at 14 degrees of freedom, and it should yield a t-star value of 2.9768. So 2.9768 times the standard error of our slope. And again, if you want to solve for standard error, you could actually run the linear regression t-test, get the t-value, substitute it in, solve for the standard error if you wanted to put a numeric value there. But our calculator is going to spit out the interval for us anyway, so in terms of support, I think it's important to note what your t-star values is at n minus 2 degrees of freedom, but you don't need to substitute in the standard error value. So we're going to be looking at an interval of 3080.3, and then on the right hand side we have 8338.2. So there is our interval for our slope. We feel that the relationship between change in runs and change in average, or total runs scored in a year, should fall between 3080.3 and 8338.2, using our B value up here of 5709. So, we have quite a bit of error on either side of that. That is exactly what your calculator spits out over here using this, and it knows the standard error, but for some reason TI calculators just don't spit out the standard error. It'd be a really nice thing. Maybe we should write them a letter and ask them to do it. So there are the mechanics of our interval. Now time for a conclusion that's in context, sparing you the expense of having to watch me write this all out. I've written it out for you. So typical conclusion, we're 99% confident that the true slope for runs scored to team average falls somewhere between 3080.3 and 8338.2 based on our sample of size 16 teams. Again, I'm going to note down here for you, this is not something that you really need to note. Since slope represents change in total runs per change of 1 in team average, the slope actually measures total runs in a year. So we could try to predict total runs in a year. And remember, we had a negative y-intercept of 706. So plugging in a value for team average, we're automatically subtracting 706, and then we're taking a fractional value of our slope. So these numbers may look large. No team scores 8,000 runs in a year, but in terms of making a prediction and knowing what your inputs are for x and your y-intercept of negative 706 kind of brings it down back to reality. And you can try that for any of the values in your table at the beginning and see whether or not they make sense. They should. They actually come out pretty darn close due to the strong R and R squared values that we have. So that is how you do inference for a confidence interval for slopes. Next page is going to take you through a problem. We're not going to really do it out. Just want to show you some output that you should be able to read. All right, so here you have, again, an explanatory response variable between mass and volatiles. I really don't know what this has anything to do with, but contextually I'm not worried about it. I'm more just trying to show you what the output looks like. So a lot of times on the AP test, they realize that going through all of the calculator steps could lead to an error somewhere along the line. And if they really want to see if you understand a problem, they're just going to actually give you the output and make sure you know how to read the output, and then go ahead and do the things that are required of it. So you've seen output like this at the beginning of the year when we were doing linear regression stuff, and we said at that point there wasn't a whole lot that you could do with it other than steal some information. So one thing I'd like to point out is if you put this data in your calculator and run regression on it, these two numbers down here should show up, because mass is your independent variable, and volatiles, I guess, is the other variable. And we're trying to see whether or not you could generate the slope and the y-intercept off of this. And in fact, down here, these two numbers are your slope and your y-intercept. Remember that the coefficient of mass is going to be your slope. Coefficient of the constant is always going to be your y-intercept. So we could write down that y hat is equal to 3.52369 plus 0.162848x. So that is your least squares regression line for this set of data, and you should be able to generate that right on your calculator. Now, the interesting thing is when you look down here at t ratio and probability, we're really only focusing on doing a linear regression t-test for slope. And that means that when you look at this, it's telling you that if you were to run a linear regression t-test for slope, your t-value would be 1.05. Technically, though, you could run a linear regression test on the y-intercept. It's a less used thing, but it's actually telling you what the t-value would be on the y-intercept for the comparison of your statistic to the parameter, the true y-intercept. We really don't care much about that because so many times y-intercepts don't make any sense in the setting of the problem. At the right-hand side, you're actually going to see the probability calculations, and I'll only focus on the one for the slope, the 0.32. And what I want you to know is when you see Minitab output, unless it's clearly stated otherwise, the assumption is that the probability that's given is for the two-sided test. So if we were looking at an HO here of beta equaling 0, the HA for this output is beta not equaling 0, which means that that is the two-sided probability, that the probability of the t ratio being greater than or equal to 1.05 or less than or equal to negative 1.05. So if you were doing a one-sided test, so if you chose to put this information in your calculator and run a one-sided test for beta greater than 0, the probability should be exactly half of that. You should be getting a p-value of 0.16. So this is the two-sided probability of 0.32. So it's going to be harder to reject the null hypothesis with this with a two-sided test. And really what you're seeing here is for a two-sided test, you're getting, this particular value larger than most alpha values you would ever choose. And it kind of makes sense because the slope that you're looking at is only a slope of 0.1628. Is that a significantly positive slope? The bigger that number gets, the more significant the slope is. So, this would lead us to believe that maybe the slope truly could be 0 under the null hypothesis. Again, the important thing is just being able to read this and understand what these things represent. The other thing that I'd like to point out that is given to you by this particular table is right here. This is the standard error of the slope. If you look, standard error of coefficient for slope, 0.1547, that is SE sub B. So when given the Minitab output, you actually know that value. So if you wanted to go ahead and run a confidence interval on this, you know your B, you know your SE sub B, you can calculate your T star for whatever interval you want to use because you know that you are working with a certain number of items at a certain degree of freedom. So in fact they come right up here and tell you that 11 minus 2 degrees of freedom is 9 degrees of freedom. So you could generate an interval off of this information as well. The only thing that I'm not giving you right now is any types of graphs. So I guess having the information over here to the left, you could generate graphs of the actual data, you could generate the residual plots, you could do the normal probability plot of the residuals, you could get all of that information from this set of data. Often on the AP exam, when they go with the Minitab output, they're also going to provide a couple of additional graphs, and they won't actually provide the raw data. So you won't be able to plug it in your calculator and do everything, but you will be able to have the graphs, or at least reference the fact that the conditional check would require a constant distribution of the residuals or a normal probability plot that is linear for the residuals. You would have to reference those things in your conditional checks. All right, so that takes you through the confidence interval. I think that there's a few problems you guys should work on, so if you go to the next page, there's a list of those. So I would say for preparation for the exam, you don't need to do a ton of problems if you follow those examples. You may want to go in and check these odd problems on these pages to make sure that you can go through and generate the proper test statistics and the proper probabilities or intervals depending on what type of question they are. Be familiar with the conditional checks. Again, 2 of them I think are pretty straightforward, that it's linear and that it's a simple random sample. The other 2, again, are based on the residuals, so you'll always be generating the residual plot, so you should be able to check those out fairly easily as well. The mechanics of the entire inference toolbox are exactly the same. Population and parameter for a confidence interval, HOHA for the statistical test. All right, if you have any questions, bring them up in class. Hopefully this was pretty clear, and again, thank you guys for a great year. Best of luck on your exams, both Mr. Brecklin's kids and my kids, on Friday. Hopefully it rains so you won't be missing anything. All right, talk to you later.